Hi, I'm Jagrat Singh, and I'm a computer science graduate student at University of Florida. I've made this project called face recognition using eigenfaces method. And why did I make this project of all the projects that I could make? I'll tell you. There are various reasons for that. In today's world, almost everything happens over the internet. There are too many electronic transactions that are taking place, and so the foremost requirement to have so many electronic transactions take place fast and securely is to have good ways of authenticating them. And the current methods that we have are pretty useful, like setting up a password or like sending emails to you to authenticate, or like asking you to remember your last security questions. But there is a scope to make things a lot better. Other ways where authorization is a problem is getting access to buildings or restricted areas. Right now, people use badges or pins to get into buildings where restriction is access is restricted to only few people. But there are loopholes, as in like I can get someone else's badge and try entering a property, because the badges are not related to every person. It's an exclusive entity. I can use someone else's badge. Someone else could use my badge. So to check this restriction, people started using biometric authorizations. For example, they started scanning people's irises, people's thumbprints, etc. It worked really well, but there are certain overheads for the user, because the person has to either like stand in front of an iris scanner, scan his or her iris, or like give a thumb impression. It's also There's also a problem for the people employing this authorization, because they need to spend extra for those specialized hardware. So in this too, like, so this is where facial recognition comes in. It doesn't require very hard or very expensive hardware. It doesn't require any overhead for the user to use it. It's very easy and convenient to use. Anyone can use it, and any webcam would do, as long as you're taking a good shot. Now I'll define what facial recognition is. The term facial recognition is quite self-explanatory, but I'll still delve into certain details. We need to understand what facial detection is and what facial recognition is. Facial detection is basically just detecting whether it's a face. It's not a car or a UFO or a lamp or a cat or a dog. So if a camera is shown a face, it needs to tell you whether it's a face or not. It's a simpler problem. Is it yes or a no? Every face has unique characteristics to them. No person looks alike, unless they're like very what identical twins. I really haven't seen them. So even if it's not visible to our eyes, there has to be certain differences. So that is when facial recognition comes in. It's a more complicated problem. We need to understand how to recognize one face from the other, and if we recognize a face, then we need to say who this person is. There are various ways we can recognize a face: by looking into the local regions and by looking into the global regions. As far as local regions are concerned, we can choose local feature analysis or Gabor wavelength. We focus more on the local regions. Generally mean your eyes, or your chin, or your ears, the color of your eyes, or like this, based on like local characteristics. On the other hand, principal component analysis, which is a global which checks things on a global area. Basically, what it does is that it's more into the relation between your eyes and your chins and your ears, etc. People also use independent component analysis. We will be using principal component analysis. It complements eigenfaces very well. To check two faces properly, we need to use the similarity measures. We can use neural networks, Euclidean distance, or template matching to find the similarity ratings of two different faces. So as far as the eigen method is concerned, I'll delve into more details. What are eigenfaces and why do we use them? First of all, they're not regular faces; they're eigenfaces. They're pretty ghostly to look at. Kind of looks like an X-ray, but still different. So once we have like a set of images, we make covariance of the matrix. I'll delve into the details properly once again. So it's to simply know they are the eigenvectors of the covariance matrix from the set of faces that you already have. They represent faces way more efficiently than regular images. And the most important the most important reasons for using them is because they reduce dimensionality. Uh, since we will be using PCA, PCA is principal component analysis with eigenfaces, it's very important for us to make sure that it's fast and it's effective, because that is the key highlight of PCA. So to reduce the dimensionality, I mean that we can represent a photo in a 2D set of points, or in 1D as a plane vector. With PCA we use the second approach. What PCA is basically it builds m eigenvectors for any photo of range m into n, m into m. It helps us find the principal component of any data, and we will find that 90% of the variance in most of the photos is basically 5 to 10% of the dimensions. It gives very good representation of the phase space cluster. Now I'll go into details of how the recognizer actually works. Basically giving you a proper overview of whatever I spoke about till now. Creating a training data set of m images, each of, let's say we need to train our algorithm as to like which faces are recognizable, and recognizable, that's the question, recognizable against what. So we create a training data set. Let's say I keep 50 images in my training data set, a different folder where these 50 images are kept, and I that is where when I create a training data set, so that I can use an image from outside and check it against one of these images if it's a proper match. If it matches one of the person's photo inside the training data set, it's a good match, otherwise it's a no match. So what goes into the training, what goes into training the data set is what I'll talk about right now. So if let's say if we have m images, each of dimension n into n, we create face vectors from each and every vector. This is the face vector. So each image is transformed into face vectors, and then we normalize it by creating an average face vector of all the images that we have. Now we have face vectors of individual faces, and we have an average face vector. What we need is derive characteristics values of for each and every face. What the average face vector generally has is the most common features of all the faces in the common database. So if we subtract the face vector from the average face vector, what we get is the characteristics that are very exclusive to that particular face vector. Okay, that is what this is, epsilon I. That is what we get. So we subtract the face vector from the average face vector, and we get the only characteristic set of values for that particular face, and it can be defined by epsilon I vector. We also need to form what is called a covariance matrix. What a covariance matrix is basically multiplication of two matrices. We have a set of vectors, the vectors that we defined over here, vector I, which was the result of the subtraction. We create a set of these vectors called A. So from this A matrix, we create something called a covariance matrix, which is basically a multiplication of A and transpose A. We need to use the covariance matrix to ultimately find out the weighted eigenvectors, but the C over here, the covariance matrix, turns out to be too big. It turns out to be of dimension n square into n square. We can't afford to have a matrix too big, of size this big, because we need our recognition happening very fast. So what we do is we use a clever way of choosing another matrix called L, where we use A only, but in a different way. We reverse the ordering from A transpose 2 multiplied by A, and we get the dimension is lowered. It's now m into m. Now we need to find a correlation between L and C, so that we can use L to find the data that we need inside this matrix. The correlation can be given by here, can be given as this, where ui is equal to A multiplied by vi. Ui is the eigenvector for C, vi can be the eigenvector for vi. Once we have this correlation, we can use L to find the data in C. What do we find over there? We find eigenvectors. There could be multiple eigenvectors stored over there, but we only need to find the k largest eigenvalues. Why does that happen? It's seen that it has been seen that only the larger, or the initial larger eigenvalues contain most of the information about images. The eigenvalues towards the end are mostly noise, so we focus only on the k eigenvectors. Once we have them, each face in the training data set is represented as a weighted sum of the k eigenvectors in the average face. So each face can have different k eigenvectors, and they basically and they're weighted because one eigenface could like contribute something to the main image, and the other could contribute differently to the face image. That's why they're weighted. So now the training data set is built. Now we focus on checking or recognizing an image. Let's say we have an input image. The input image is again, we follow a similar method, however we train the training set, but here we'll see there's a difference. The input image is again converted into face vectors. The face vector is again normalized by creating an average face in the subtraction that I spoke about earlier. Once we do that, we find the covariance matrix, and from that we represent the input image as a weighted sum of the k eigenfaces. So now what we have is we have a vector representing the weighted sum of the k eigenfaces of the input image, and we did the same thing for the training set. So we find the distance between the input eigenvector, the input weight vector against all the weight vectors of the training set. Okay, so we find the distance, and this distance is where we decide whether it's a match or not a match. If the distance d is less than a threshold, by the way, we define what the threshold value is. So if the distance d calculated is less than a threshold, it's a known match, as in this unknown input image matches to a known image present in the database. If it's not, if the d is less than threshold, then it's not a match, it's something else. Alright, I'll go on and show you a demo of what I just spoke about. So I'll go inside. First of all, I need to show you what I kept in the training database. If these are the images I kept in the training database. So, and these are the images I'll be testing them against. These images are not present in the training data set. So what I need to do is I need to go and start the system. Wait, so it's already here. So let's say I choose a face. Which face should I choose? Let's say I choose a face over here, probes. Let's say I choose Amy3. So Amy3, as you can see, is not present in the gallery. We have photos of Amy where Amy is not smiling, but here Amy is smiling. I got the database from AT&T. It's for public, for research purposes. It's available to everyone. So here she's smiling. We'll see if our algorithm can recognize her. So I choose Amy3 from the folder probes over here, and it will be tested against the training set, which is in gallery. So I decide what the threshold value would be. So here I know it's there, so I'll just decide the threshold value of 1, and I choose 10 eigenfaces. That's also an input. So I click match, and as you can see, it has matched. The photo in the probe has matched with the photo in the training data set, so it's a good match. So now we gotta show something which doesn't match. So let's say what should I choose? Let's say I choose Gabe. I think that is how it's pronounced. Gabe. I choose Gabe. It's not present over here in the gallery. There's no Gabe. So I go back, and this time I'll choose Gabe. How do I do that? I'm already in the folder. I choose Gabe. Any other photos doesn't matter. I keep a very low threshold so that it was fine, and I match it. It doesn't match. No match. Try higher threshold. So I think that pretty much gives you a good idea. I can show you how the eigenfaces look like. The eigenfaces have been there's a folder created for the eigenfaces. Pretty ghostly to look at. So here they are, eigenfaces. This is how they look like. Boom. Here and here. These are the eigenfaces that were constructed for the facial recognition. So I think that'd be enough. I think we used eigenfaces, and we found out a lot of things about them. They work really fast in real time. The facial recognition happens very well. There are certain pre-criteria that one needs to look at. The faces that we use need to be properly lit. They need to be centered, and if these two things are taken care of, well, we're good to go. Alright, so thank you so much. I'll be ending. Alright.